Hi, this is Mike Lawless, and in this video, I'm going to show you how to use ADMET Modeler. I'm using ADMET Predictor version 10.3 for this tutorial. I've read in 100 compounds from a SPILES file. The dependent variable is the solubility underscore mg underscore ml. So this is a solubility in milligrams per milliliter. And I'm going to pin that column. That is the endpoint I want to predict. I'll undisplay a couple of these columns just to kind of clean this up a little bit. The first thing you want to do when you read in a data set to start building a modeler is go through the chemistry options here and neutralize all the compounds, standardize the functional groups, and standardize the tautomers. I've already done those steps for this data set, so it's ready to go. The next thing I'm going to do, since this is in milligrams per milliliter, is I'm going to convert it to molar units. And in order to build the model, and build a model in molar units, and then transform them back to milligrams per milliliter. That's the way we built the S plus SW model. So the first thing I want to do is calculate properties for these molecules. I'll just use all the defaults and click calculate. And then I'm going to come in here and right click on insert column and insert a new compound attribute. So this will be the solubility in molar units. I'm going to use the solubility in milligrams per milliliter. So I'm just building this equation. So I double click here to build the equation up here. And then I'm going to divide that by our molecular weight descriptor, MWT. Again, I double click, so that's saved in there. And I could save this in a file, but it's a pretty easy equation, so I'll just put it in here. And then I want to look at the least soluble, which are these two compounds, about 10 to the minus 8 molar, and then sort in the other direction. So this is the most soluble compound with 1.9 or almost 2 for the solubility in molar units. And then I'll click a third time just to sort it in regular order. You always want to look at a distribution of the data, so I'll just create a distribution plot here. Click on this, and I'm going to use log units here, and then apply or click OK. And you see that the lowest one, as we mentioned, had a log solubility negative 7.4, and then it all goes up to a log of solubility about 0.3. And this is a nice distribution. Okay, so we'll double click on that graph to redock it, and then we're ready to start building our models. Usually I just click on this icon here, the ADMET Predictor icon. You select your dependent variable, which is the value you want to predict. So here, solubility underscore M. If we had any test sets defined, it would come along here, and then we could use the same test set over and over again. I'll just click OK. That will bring up the first ADMET Modeler dialog box. So we have the dependent variable here selected as normal. For the reference variable, I'll talk about that later. This is only if you're doing a delta model. And here we're just trying to predict the values in this data set. We're not going to use a reference model. We want to logify dependent variables, so we convert this to log space and build the model there. Now, by default, we put all of our descriptors that we calculated when we calculated ADMET properties over on the right-hand side here. Over on the left are mostly models or other input fields. For this particular model, I want to include S plus log P. Now, some QSAR purists don't like building a model using models as descriptors, but here I think log P is always it's correlated with solubility, so I'm going to go ahead and use that as a descriptor in there. Then click on the next button. So this dialog leads you through a series of steps to set up the ADMET modeler run. By default, we're going to create an artificial neural network regression model. This is typically what we use internally to build our models. Other options are support vector machine, kernel partial least squares, and multiple linear regression. Next, we want to select the test set By default, we use a Cajonan map. Here, I'm going to change that. Something we've been doing a little more recently is using a stratified sampling by partitions, and we're going to use random sampling. And then we're going to use a 20% test set. Now, normally, when we build our models, we use anywhere from 10 to 20%. The data set goes into the external test set. So the advantage of this stratified sampling, what it does is kind of bin the data based on the variable you select here, and then select a few of the compounds from each one of the bins. So here we're selecting a minimum test set of 20% of the compounds. So we'll create these bins and then randomly select however many compounds it needs from each one of these bins to create the test set in there. And what this ensures is that the data in the test set is going to be distributed in the same manner as the training set. One thing you want to avoid is having the test set values all clustered together and not give you the full range of experimental values. So just click OK on that. Under the descriptor selection, this is what we use for selecting what descriptors go into our models. So with ADMET Modeler, we're going to build artificial neural network ensemble models. A priori, we don't know how many neurons or inputs or descriptors are going to create the best model. So we're going to create a grid and then select the best model based on the statistics from the grid. And what this does is it's an algorithm for selecting the best descriptors for, say, a 10 neuron model or a smaller set of model. Now, these are kind of arranged in order of speed. So truncated linear analysis is the fastest method. That's why it's the default. Iterative truncated linear analysis is second. Input gradient is third. And then genetic algorithm is the slowest, but it's a very good algorithm. And I'm going to select the option to do the cells. So this is going to reselect the descriptors for every cell in our grid. So every new model, it goes through this procedure to select the best descriptors. Then simply click Next. Here's where we're setting up our grid to create for the model. So if I click on autofill, it's going to fill in some of this, and it's trying just to build a nice square matrix of models to build. And so typically I will change this up a little bit. In this case, I'm going to go from 1 to 7 neurons with a step of 2, and then a minimum of 5 and a maximum of 72. That's a little bit overkill, but you'll see that it doesn't create a model if there's too many descriptors involved in neurons. So it makes it too complicated of a model. And then I'm going to go with a step of 5. So this is going to create a 1 neuron 5 input model, then a 1 neuron 10 input model. So it'll step the inputs by 5. And then once it reaches the number of descriptors, gets all the way up to 72, then it will increase the number of neurons to 3 in this case, and then step through these again. By default, we build 165 neural networks and pick the best 33. So 33 times 5 is 165. So it creates 165 total. And then it will select the best 33 of those. We're going to use Monte Carlo algorithm for the starting points. These are the coefficients that are used in the A and an E model. And we're going to, that's based on a random number. And that's why each one of the models can be slightly different from each other. Then I'm going to go into the summary. This just kind of summarizes all of our options. We can click on some of these to expand these. And then I'm going to click Build. Now here's where you have to give it a name of the project. By default, it is the name of the input or endpoint, then the date that you're performing the model build, and then it appends _01. We'll go ahead and keep that name, click OK, and then it starts building models. So I'll pause the video till this is finished. Okay, so that took under a minute, probably 45 seconds to build all these models. And I'll just expand this a little bit so that you can see all of the models it built. And you see that it didn't build some of these models in here. The reason is that it was too complicated. So if we go under Tools, Number of Weights table, you can see that when you get up to 25 inputs, a 3 neuron model, then you have 82 weights that you're trying to solve. And one of the earlier dialog boxes said that if you get above 70%, 75%, in other words, if this is 75% of 100 in this case, so above 75, it's not going to build that model because it deems it too complex. Then by default, it highlights what it thinks are the best models. So if we go under the Tools, Best Ensemble settings, this is the algorithm it uses for selecting the best model. And it's based on the verify training and test set statistics, root mean square error, Spearman's rank correlation coefficient, and Q squared. So it basically evaluates each one of the models based on the scoring function. We can click on this to see what the scores are. So the best model is this 5 neuron, 5 input model, and the dot score is 0.87. So for this particular build, this is by far the best model in here. We could change this criteria if we wanted. So the easiest thing to do is click on this button to just pull up what's known as the P&O file, or the predicted versus observed file. A lot of times I like to switch the axes and look at observed versus predicted. And as you see here, it's got a nice slope close to unity for this particular model. And then we have some outliers, but this is part of the training algorithm. The red points are in the test set and the blue points are in the training set. So we can take a look at those individually by turning off the other one. We can also look at the diagonal, etc. In all models, though, you want to look at how the predictions are on the external test set, and that's a way of validating the model, making sure that it's not overfit for this. So if we look at this model for the root mean square error, this top number is the root mean square error for the training set. This is the value in red is for the test set. And you want those numbers to be fairly close together. So some of these models out here where you're getting a root mean square error of maybe around 0.93, but the test set is much higher, those are kind of less desirable models. So what I would do at this point is I would save the project, click Save, then go into a specific directory, select a folder, and save the project file there. Now, when we look at this, our best model is a 5-input, 5-neuron model. But you see, it didn't explore a 4-input, 5-neuron model. So I typically like to go back and kind of fill in this grid a little bit here. So maybe go from 3 to 7 neurons, and then maybe 4 inputs up to 10 with a step of 1. So I would just go into the model settings, go into the previous dialog box, highlight the first cell here, type 3, then tab is usually the easiest way to go over. Set that at 7, go by a step of 1, go from 4 neurons to 10, or excuse me, 4 inputs to 10. An input is a descriptor. And then a step size of 1, go back into summary, and then click build. Now this time it's incremented the last number on the name, so we can save that, click OK, and now it starts building models again. And we'll just let this go to completion. It shouldn't take very long, but you can see how fast it's working down here, kind of in the summary. And you see that our old model was about a root mean square of 0.8, so that's what we're trying to build, beat with this model. Okay, almost finished. Before we proceed, let's take a look at the log file by clicking on the button View Log File. I should have went over this for the first model build. This is the log file. It's saved with the project, and we can pull it up at any time. So it gives the number of data points, the DAT file, which was created, and then looks at non-numerical inputs. Any inputs that have a correlation variance less than 1, it would throw out. It looks at underrepresented descriptors. So this descriptor is the number of bromine atoms, and there's only one molecule in there with a bromine atom. So that's underrepresented. And it's not going to be able to differentiate between the variability and solubility in this data set because there's only one point where it's 1 and the rest are 0. So it throws that descriptor out. Then it looks at correlated descriptors. So here it's comparing molecular weight to the number of electrons. Pretty good correlation there as you'd expect. So it would throw out one of those two descriptors because you don't want highly correlated. So either one or the other of these descriptors would be thrown out. Then it lists the candidate descriptors, so log P, etc., going down here. And then once it's finished that, it shows the default setup, or excuse me, the setup of this particular run. So that's in there. It tells what points are in the training, verification, and test sets here. Then we start building models. So it tries to select the best descriptors for a 3-neuron, 4-descriptor model, and it's selected these 4 descriptors here, and then so on and so forth for all of the models that we built within this grid. So let's go ahead and turn that off. Now, I will go ahead and save this project. So click Save. It takes us to the same folder as the previous project was saved. So I'll click that, and then that will save there. Now, I don't know if you remember, but the old model, the previous model had an RMSE of 0.71 for the test set, and none of these here achieve that. Both model builds had the same test set, so you're really doing a apples to apples comparison here. So let's go back and open the previous project. So if I go File, Open Project, and then navigate to the PRM file for the previous one, you see that this is root mean square of 0.71. Lower values are best. So we'll go ahead and click on this to see the grid. Now, typically for our notebooks, we would copy this image to the clipboard and then maybe save that in a PowerPoint file. This also allows you, if we were going to do a third run, to compare that run to this particular run. So that all looks pretty good. So what I want to do is make this model available for prediction of other molecules. So I'll right click on this cell here and select Export Model. I have to give it a name, so I'm going to say just give it Solubility Model, something very simple. I don't believe you can have spaces in this. It knows that we transform the data by taking the log of it before we built the model. So this transform is going to take the anti-log to return it to linear space. This is the net file. The format is the name of the model, run, and then _5 are the number of descriptors, and then the last one are the number of neurons. So this is a 5 input or 5 neuron, 5 input model. We're not going to select a minimum and maximum, but these would be the maximum and minimum numbers that would return if the value was outside the scope. So in other words, if I set a maximum solubility of 2, but the model you actually return 3, then in ADMET Predictor it would only display 2. Okay, the auxiliary factor is going to transform the output of the model, which is in molar space, back to milligrams per milliliter. So here we want to select MWT as the auxiliary function. So by default, it'll output the value in milligrams per milliliter and multiply it times, or excuse me, in molar units, multiply it by molecular weight to transform it into milligrams per milliliter. And then for the tooltips, let's just write solubility model based on 100 compounds in milligrams per milliliter, and then click Save. Now, if we exit ADMET Modeler simply by clicking on the X and then go back into ADMET Predictor, it knows that the model database has changed. In other words, we added a new model to the bottom, and it asks if we'd like to recalculate the ADMET properties. So let's go ahead and click Yes, and it will calculate the new values here, and that will be the solubility model that we've added. So again, let's pin this column here. get it next to the solubility model. And then let's create a quick heat map of everything here, and then sort in milligrams per milliliter. Move this over a little bit, and then just compare a few of these values. And you see they're not far off. This one's quite a bit of an outlier here. If we take the scatter plot and let's plot solubility in milligrams per milliliter, so that's the observed value, and then our new model here, which is simply solubility. These are listed in alphabetical order. So we click here and then apply that. Now let's do a log plot in milligrams per milliliter. So this is the kind of predictions we're going to get out here. Make that a little bit bigger. And then if we highlight this and highlight that, that's one of the larger outliers within the system. So that's the basics of building a model. In the last section of this video, I'm going to quickly show you how to create a delta model. So with the delta model, you're taking our current global model, comparing it to your experimental values, and typically you're going to see a larger RMSE than you would expect from our model. So you'd like to build kind of a local model, but also incorporate our data within that. So that's how we build a delta model. So again, I'm just going to click on the ADMET modeler icon, choose the endpoint that corresponds to the values from the experiment. I'm going to define the reference model as our SIP RLM clearance model. So that's what the input data is based on. And then logify that. I'll use the S plus log P as a descriptor here, so push that over. And that's the basic setup for a delta model. We'll go through some of these other options. Let's, instead of using a Kahona map, let's use randomized stratified sampling as we did before. And then instead of truncated linear analysis, let's use a GA per cell algorithm. So we click OK, and then next, we'll set up the grid. I'll just go with the grid size. This is a pretty small data set, 31 observables. So we have a pretty small grid here. And again, I'll increase the number of Monte Carlo tries for the starting point, and then click on the summary, and then finally on the build. I've got some funny parentheses in here and back or slashes that you can't have in the name of the model because it's going to try and save this as a directory. And so I'll go ahead and just replace all those with underscores and then start the model building process. And you see we get some pretty nice models in here. This one has a root mean square error of 0.13 for the test set. And that's really what you want to compare. So if I click on that, this graph shows the delta model. So this is the model that's taken our predictions, used the error model, which is really what you're building in this set, to come up with the overall predictions. And you could compare this to the reference set here. So if I click on reference set, these predicted values are simply from our SIP RLM clearance model. And you can see that performs not as well as the delta model. And then the error model, here's where we're trying to correct the predictions from the standard local model here. So that just sets up the delta model. And then again, you could export this and save it as I showed for the previous model before. So that concludes the video on building models with ADMET Modeler in ADMET Predictor. Thanks for watching, and I'll see you next time.